Math 2414, Trigonometric Substitutions, Video 5, another type of trig substitution. In the videos prior to this, we developed a technique for integrating an expression that contained the square root of a constant minus x squared, and some variations on that. And we ended up using x equals some constant times sine theta as a substitution, but the motivation behind it was to take advantage of a trig identity that collapsed the subtraction problem down to a single term. Or more generically speaking, collapse the binomial down to a monomial. So we're going to do the same thing here. Now I do want to point out that trying to do a straightforward u substitution on this will crash and burn really quickly, because your substitution would probably be u equal x squared plus 1. You have du equals 2x dx. In an effort to build the du package, there's no x anywhere. So that substitution would fail. Now, that doesn't mean you shouldn't try it. I mean, you can try it and it'll fail, but if you don't have a plan of attack, try something. If it works, great. If it doesn't work, then try something else. If we're going to take advantage of the same approach as before, then we need to find a trig identity that kind of resembles the addition problem structurally. In other words, we want a trig identity that has something squared on the left side of a plus sign and a constant on the right. Well, I know one. I know that tangent squared theta plus 1 is equal to secant squared theta. And so, if we match our addition problem with that addition problem inside that identity, then we know exactly what we want to match up. We need x squared to become tangent squared theta, which means we need x to equal tangent theta. And again, when the time is right, and I believe that's video 7, we'll categorize this approach, but let's kind of figure it out first. All right, so based on trying to match the addition problem to half of a Pythagorean identity, we're going to try x equals tangent theta. Let's try it. All right, so we're going to use x equals tangent theta. And I want to remind you that when you're doing a trig substitution and you've determined your substitution, there are two things you need to do with it. Number one is to take its derivative, of course. dx is going to equal the derivative of tangent, which is secant squared theta d theta. But you also need to draw a triangle for your trig function. Well, how can we draw a picture of x equals tangent theta? By drawing a right triangle, putting theta in one corner, and then remembering that tangent is opposite over adjacent. So we need to label the opposite and adjacent side so that tangent is equal to just x. That would be x over 1. In anticipation of needing the hypotenuse, if we did the Pythagorean theorem, we would get the square root of x squared plus 1. Not a coincidence that that is also the square root inside the integral. All right, so determine your substitution, differentiate it, and draw the picture for it. And let's see what happens. All right, each x is going to become a tangent, so under the square root we get square root of tangent squared theta plus 1. dx is equal to secant squared theta, and now we've turned it into a trig integral. Let's see what happens. The purpose of the substitution was to capitalize on tangent squared plus 1 being secant squared. So we get the integral of the square root of secant squared of theta times secant squared of theta d theta. Well, the square root of secant squared is secant, so that secant multiplied by the secant squared will give us the integral of secant cubed. Well, here's one that we saw before. When we did the trig integral series of videos from last week, the integral of secant cubed was a special one. It required splitting it using integration by parts and then running into the recursive scenario where the integral of secant cubed showed up again. But since we've done that problem, we're going to go ahead and categorize it as something we have an answer to. If you don't remember the answer, then you need to remember the approach for getting the answer. But let's just say that we know the integral of secant cubed is 1/2 times the quantity secant theta tangent theta plus natural log absolute value of secant theta plus tangent theta. However, if you would like to review that video, then go into week 2 module. This is for those who are in my current class. Go to the week 2 module, find this video, and go to the, I had the time mark, let me go back quick, the 7-minute and 32-second time mark, 7:32, 32. And even if you're not in my class, if you search that title on YouTube, it should take you right to that video. I would leave out the 16 minutes and 27 seconds and then go to the 7-minute and 32-second mark if you want to see details behind the integral of secant. But let's finish this problem. We now have our integral, or at least the answer to it, so the antiderivative, if you will, in terms of theta, but we need it in terms of x, and this is where the triangle comes into play. Because this expression is so lengthy, it might be beneficial to the side of the triangle to just jot down what secant theta and tangent theta are. Actually, we know what tangent theta is because tangent theta was what our substitution was. But we do need an expression for secant of theta. Secant of theta is the reciprocal of cosine. Cosine is adjacent over hypotenuse. So secant is hypotenuse over adjacent. And in this triangle, hypotenuse over adjacent is just the square root of x squared plus 1 over 1. But why bother putting it over 1? So that's going to replace secant, and x is going to replace tangent. Let's write our final answer. 1/2 times the product of secant and tangent. So we can put the x and the square root of x squared plus 1 right next to each other. I know secant is square root of x squared plus 1 and tangent is x, and I reverse the order, but it's a multiplication problem. And plus, don't ever stick stuff after a square root if you can avoid it. However, don't close off your parentheses too prematurely. Plus the natural log of the absolute value of secant x plus tangent x. So square root of x squared plus 1 plus x. Close the absolute value, close parentheses, don't forget the plus c. A little bit too far outside there. And the problem's over. Is this a messy problem? Well, of course it is. But as I warned you in a previous video, we are arguably in the midst of the most difficult part of this course. Trig integrals. Excuse me, not trig integrals. Trig substitutions, which lead to trig integrals, and undoing the trig substitution. Let's take a look at another one. We'll kind of figure out the substitution, and then we'll categorize when to do this